Let's take another example. Y is equal to 2x plus 1 over 2x minus 1. To get the vertical asymptote, we try to find what makes the denominator 0, and of course we know that it'll be when x is equal to 1. And we take the limit of 2x plus 1 as x approaches 1 coming from the right. When we plug in values of x close to 1 from the right, this will remain positive, and this will be close to 0 in a positive sense, so the limit is plus infinity. On the other hand, if we take the limit of 2x plus 1 over x minus 1 as x approaches 1 coming from the left, we are plugging in, trying to approach numbers where the x's approach 1 from the left would be 0.9, 0.999, etc. This still remains positive, but the denominator goes to 0 through negatively small values of getting close to 0, so that the reciprocal will be, or the ratio would be, approaching minus infinity. Okay. Now, to get the horizontal asymptote, we check the degree of the numerator and the denominator. Since the limit of 2x plus 1 over x minus 1 as x approaches infinity is 2 over 1, which is equal to 2, then y equal to 2 is our horizontal asymptote, and x equal to 1 is our vertical asymptote. Okay? So what we can do is just to plot a few points. Say if x is 0, y is negative 1. So right here. If x is, let's plot a few points right here. That way we'll know how to graph our function. So let's say x is 0, our y would be negative 1. If x is, say, negative 1, then this becomes minus 2 plus 1 is a minus 1, and that becomes minus 1 over minus 2 becomes a positive 1/2. So what we have is the graph will approach our horizontal asymptote. Okay, and in this other side it'll approach the vertical asymptote, where it goes to minus infinity as I approach 1 from the left, and it approaches plus infinity as I approach 1 coming from the right. And naturally, as x approaches plus infinity, the graph approaches the horizontal asymptote. That's when y is equal to 2. Okay? So that completes the graph of the function 2x plus 1 all over x minus 1. On page 90, in example 11, we have these several rational functions which illustrate that they can behave in different ways near zeros of the denominator. If we want to evaluate the limit as x approaches 2, we try to factor this, and we see that I can factor the bottom by the difference between squares, so it'll be x minus 2 times x plus 2. And that will give me a chance to cancel out one of the x's. One of the binomials. Will be cancelled on the top, so that would now be, that cancels out x minus 2, and we take the limit of x minus 2 all over x plus 2 as x approaches 2. That's just 0 over 4, which is equal to 0. Okay, So just because you have an x that makes the denominator 0 does not necessarily imply that you're going to get a plus or minus infinity as you approach a number that makes the denominator 0. This is the case where you have a removable discontinuity. Okay, but what about as x approaches 2 in this particular case? Well, let's look at the top. It's just x minus 2 all over, the same one as in letter A. So we factor that out and this gets cancelled. Okay, and then we take the limit of 1 over x plus 2 as x approaches 2 and we get a fixed number 1/4. Again, this is the same case as A where we have a removable discontinuity. Okay, what about letter C? We look at the limit as x approaches 2 from the right. Okay, how do we do that? Well, we will just examine the signs when we approach 2 from the right and find out whether this is getting close to 0 in a positive way and what is the sign of this number or this quantity and this one. So if I let x approach 2 from the right, this will still be negative and this will be positive and positively close to 0. So negative divided by positive is close to 0 will approach minus infinity. On the other hand, if we take the limit of the same one as x approaches 2 coming from the left, then that means, okay, this is still negative, so this is negative, and then this is negative, and that is just some positive value close to 2 for the x. So negative divided by negatively close to 0 will give us plus infinity. So based on C and D, we take the limit as x approaches 2, we say the limit does not exist, and here's when a vertical asymptote occurs at x equal to 2. Okay, now let's look at letter F. In letter F, we have 2 minus x divided by x minus 2, and if I factor out the negativity from the top, I'll get negative of the quantity x minus 2. We can see that we can cancel out one of the factors from the bottom and the top, so we are left with taking the limit of negative 1 over x minus 2. And if we let x approach 2, whether you're coming from the right or from the left, this will always be positive because it's squared. So it gets close to 0 in a positive way, and negative over a number close to 0, approaching 0 in a positive way, will give us minus infinity. So the limit of this expression is equal to negative infinity. Okay? So in parts A and B, the effect of the 0 in the denominator at x equal to 2 is cancelled, okay, because the numerator is 0 also on the top, and that's why it's cancelled by the factor of x minus 2. Okay, thus a finite limit exists. But this is not true in part F, where cancellation still leaves a 0 factor in the denominator. You see, right there, as well as in C and in D. Okay, so the main thing to do is we take the limit as x approaches whatever makes the denominator 0, and then find out whether a limit exists or it does not exist, or they approach plus or minus infinity.